Welcome to the Monday seminars, everyone. Nice to see you all. We're very lucky this week to have Qingyu Wang joining us. And she is joining us, in fact, from Vienna. She's in the process of moving, I think, from MIT to other institutions and doing other work. But she's going to talk to us today about what makes low frequency earthquakes. Just like to say that, just like to remind people that it's not that much fun to give a talk into your computer screen. And one benefit is to have a real discussion afterward. So write down your questions and please prepare yourself to be involved in a discussion. We've been quite lucky in the seminar series that it's been very easy to have a nice discussion at the end of talks. And we will have kind of up to 30 minutes, depending upon how long she talks. So I just invite people to turn their microphone, turn your microphone off right now. What you do with your camera is up to you. I like to leave mine on to, I don't know, in case Qingyu's looking at us, we're not just all blank. I'm not sure if that matters or not, or if she's looking at us when she talks or not, but yeah, that's what I'm going to do. So without anything further, I'll turn things over to Qingyu. Thank you very much for joining us.
Thank you, Chris. Thank you, Chris, for the introduction. Good day, everyone, and welcome to the talk. Today, I'll be talking about low-frequency earthquakes, specifically focusing on a case study in Japan. This study involved effort from William Frank at MIT and Rachel Abercrombie at BU, and contributions from Obara-san and Kato-san from ERI Tokyo University. We know that subduction zone usually host large earthquakes, which cause major damage and loss of life. This schematic model of subduction zone highlights the variety of faulting regimes operating at the plate interface. In the Nankai trough in Japan, instead of regular earthquakes, there has been numerous slow earthquakes observed. They play important roles in alternating stress states within the tectonic cycles. However, our understanding of the mechanics behind those slow earthquakes remain limited. Low-frequency earthquakes often accompany their slow slips and offer an opportunity to investigate the physical conditions of the plate interface. Their distinct spectral features set them apart from a regular earthquake, prompting us to explore why low-frequency earthquakes are different from regular earthquakes and what makes them low-frequency. So during today's talk, I will try to dissect this question by studying some source properties of low-frequency earthquake and the structural control of their source region. I start by outlining what we are exploring today. Firstly, I will provide a basic introduction to low-frequency earthquakes. After that, we'll explore the local seismic structure along the LFE region. This aims to uncover any unique seismic structural characteristics regarding seismic velocity and attenuation. Lastly, I will introduce a new method, the empirical attenuation function method. This method allows extracting a combined precise local path information and offers a valuable tool for studying source properties of earthquakes. So let's start with the basic question: what low-frequency earthquakes actually are? When we examine these events, they present as impulsive seismic signals that occur in a manner similar to an earthquake swarm. The click doesn't work. Okay. Typically, they have small amplitudes and short durations. They are distinct from regular earthquakes and usually associated with slow slips. If we check the accumulated number of LFEs over time, the blue curve, Frank et al. Found that the activity of LFEs is intricately linked to the slow slip events. shown by the GPS surface motion in black. In this Mexico study, they observed a significant surge in LV activity that is coincident with a slow sleep event in 2006. Given that LV manifests as impulsive seismic events, they offer us with a high-resolution perspective to disclose the intricate physics of slow earthquakes. So, as I mentioned that LVs are a typical seismic event, what are the exact differences compared to regular earthquakes? If we check out the waveform, here I plot one regular earthquake and two LVs of the same magnitude, 0.5. We see that for the regular earthquake, there is clear onset of P arrivals and S waves, while LVs distinctly showcase S wave pattern only without clear P arrival. Now, if we see the spectral behavior, here are the displacement spectra of the event in the left panel. What's fascinating is that the black curve, the LV, they display higher amplitude in low frequencies than the regular earthquake in red, while they have a rapid decrease in higher frequency content. This decrease happens much faster compared to these regular earthquakes, especially for a frequency larger than about 5. Hence, the apparent corner frequency of low frequency earthquakes is notably smaller than that of earthquake of similar magnitude. These features contribute to a distinctive scaling nature of LRVs. Here comes an outstanding question. Why are they low frequency? Is it primarily due to some robust near-source attenuation that result in a strong decay in high-frequency content? Or could it be attributed to distinct source properties that inherently limit the generation of strong high-frequency signals? Or both, or like there's a combination of both factors, a unique attenuation structure plus different source properties that collectively distinguish LFE from regular earthquakes? We don't know. Then we try to dig into these questions during this talk. To understand these underlying reasons, let's turn our attention to the Nankai region, a location abundant in both regular and low-frequency earthquakes. This study region in Nankai Trough is outlined by the red shaded zone. Within this defined area, here is the spatial distribution of regular earthquakes over a span of 15 years. I only plot the earthquake greater than magnitude 3, otherwise there's full of earthquakes. These earthquakes span varying depths, as you see, from the shallow subsurface to around 70 kilometers deep. When we check the spatial distribution of LFEs, a distinct belt-like pattern emerged, predominantly occurring at depths around 30 to 40 kilometers. Interestingly, there is an observable LFE gap here beneath eastern Shikoku Island. This gap is documented in the JMA catalog and has been further confirmed through recent joint analysis using both permanent and temporary observations. So considering the spatial distribution of both regular and LV earthquakes, we focused on two specific depth columns to make a comparative analysis on the local structure. Each depth column is of a 10-kilometer radius directly beneath two seismic stations. In one depth column located in the gap area, there are no LFVs. We refer to it as the blue column. The seismicity displays a balanced depth distribution of both crustal earthquake and intraslab earthquakes. Another depth column with LFVs show an intriguingly unique pattern of seismic activity. Here you can see earthquakes are situated in a distinct arrangement salvaging the occurrence of LFE at the plate interface. We refer to this depth column with LFEs as orange column. If we take a look at these events over time, we see clearly that there's almost no LFE in the blue column, while in orange one, LFE are consistently situated between crustal and intraslab earthquakes, showing some periodic cluster features. These regular earthquakes with good depth distribution can therefore help us resolve the local seismic structure to see whether there is any structural differences between the two columns or not. So first of all, to investigate the vertical structure, we begin by relocating the regular earthquakes within each of the two columns using the group-classed method. We use both P and S wave among 8 stations in the blue area and 11 stations in the orange area. For 1 second window length in 4 to 8 Hz frequency range, and set a correlation criteria of 0.7, we are able to relocate over 300 earthquakes in the blue column and 400 earthquakes in the orange column. The relocation result here you see colored in blue and orange produce really negligible difference in epicenters compared to the initial location in black circles. So they are consistent with the known quality of JMA catalog. As for earthquakes, regular earthquake larger than magnitude 1, JMA has these manually peaked faces, ensuring the initial quality of the hypocenters for most of the earthquakes that used in this study. The relocation doesn't change the depth range between crustal and intraslab earthquakes, hence no further constraint on the depth range of LFEs for us, but we are able to solve the velocity structure for the 2 depth columns based on this relocated regular earthquakes. With these regular earthquakes, we then invert the 1D seismic velocity structure for both columns using manually picked P and S arrivals. When checking the VP-VS ratio, we see that there is a notable high ratio anomaly existing just above the plate interface in the orange column, particularly within the LFE source zone, while the blue column shows a relatively increase of ratio above the plate interface, but the absolute value is smaller than 1.8. Doesn't show similar strong anomaly as in the orange cylinder. This ratio anomaly actually results from a subtle decrease in S-wave velocity here, just above the plate interface. Usually, a fluid-filled material tends to exhibit higher VP-VS ratio compared to some solid materials. So the high VP-VS ratio in the LFE source region suggests the presence of fluid. And this observation aligns well with previous reports associating the increased fluid pressure with the occurrence of low-frequency earthquakes. Following the velocity structure, we then investigate the local attenuation to see if there is any strong attenuation happened within the source region or FEs or not. We first derive a path integrated attenuation from the displacement spectra using all the events that we relocated in the 2 columns. Then we invert the local quality factor Q over depth, both QP and QS jointly inverted. Similar to the velocity structure, the QP-QS ratio also exhibits a pronounced anomaly larger than 1, just above the plate interface, only within the LFE source region in the orange column. Both anomaly of high VP-VS and QP-QS suggest the presence of a pore space saturated with fluid, potentially stemming from the dehydration reactions beneath. In addition to the source zone anomaly, in the orange column, we see that the ratio gradually decreases moving upward, reaching to an average value at approximately 15 kilometers above the plate interface. Coinciding with this decrease, there is a notable increase in absolute QS at shallow depth. This QS may suggest the existence of an impermeable layer above the subduction plate near or at the base of the upper plate that help maintain this hypofluid pressure within this source zone. This barrier acts likely as a key ingredient in generating the structural anomaly in the LV source region. Now we see there is a clear difference in the seismic structure of both velocity and attenuation within the two columns, but how much this local attenuation can contribute to the LV's spectra. To answer these questions, let's come back to the source property analysis. There you see this displacement spectra, including all the regular and low frequency earthquakes in both columns, and have been categorized by different magnitude from 1 to 4. And for low frequency earthquakes, they are all below magnitude 1. The black curves are LV spectra only from the orange cylinder. Once again, we observe that the low frequency earthquake component, the low frequency component of LFEs surpass those of regular earthquake within even 1 to 2 magnitude range. The high frequency range really decay fast and get to the almost the noise level at about 25 Hertz. So to evaluate how much the high frequency content of LFEs has been attenuated, we designed a method using the co-epicentral regular earthquakes that travel through the LV source region and received by the same seismic station to extract the path and attenuation information. This new method is a 6-step empirical attenuation function method, which aims at extracting precise local seismic attenuation and path information. I've introduced these 6 steps using a series of processing examples. Now let's navigate through steps to uncover its potential. The first step is earthquake relocation and clustering. As shown in A and B, I've previously mentioned in the relocation result. Additionally, we've clustered those relocated earthquakes based on both PS wave correlation coefficients, emphasizing clusters only with earthquakes number at least 10. It's worth noting here that within a narrow depth range, we can see that earthquake can belong to different clusters, and events within one single cluster can exhibit considerable differences in magnitude. And for the next step, we will use all the big earthquake larger than 2.5 as a target earthquake for a classical EGF method analysis. So the second step is the empirical green function, the EGF method. The objective of this step is to gather some prior information on the corner frequency for this target large earthquakes. This figure shows the waveform of 1 target earthquake and 9 EGF functions from the same cluster. Below is the 9 spectral ratio of them. Through this step, we get spectral ratios for all target events, and simultaneously, we are able to retrieve the source time functions. For the source time functions, we see that there is a gradual increase in duration with a rise in magnitude for this target earthquake. It's important to highlight also here that the method of group cluster, since it turns the earthquakes into clusters. Therefore, it can serve as an effective event selection tool for the EGF method data preparation. So this is the second step. Then we perform a probabilistic inversion using the obtained spectral ratio for each target event. This process allows us to obtain a probabilistic distribution of the corner frequency of both target events and EGF events. As shown by this histogram, there is a higher probability at around 10 Hz for FC1, the corner frequency for the target earthquake. And this probability of a corner frequency FC1 provides the prior information for the next step, a inversion using single displacement spectra. As we know that for single displacement spectra, there's usually this strong trade-off between the corner frequency and the attenuation term T star. So the prior information from last step can well help constrain corner frequency FC1 and address the compromise between the corner frequency and the attenuation T star. So as you see, this step provides a precise T star with the prior information and an updated corner frequency for all the target earthquakes. So the next step is the side effect evaluation. As we know that there's side effect really strong close to station, that we need to correct this side effect to have a better precise T star and corner frequency. So we evaluate using all the events received by each station. We take the average residual that between the model spectra and the row observation as an indicative of local side effects. As shown by the red curve here, it's not flat in frequency and can bring some uncertainties on short-term inversion analysis. So this step estimates the side effects, and we correct row spectra by subtracting the mean residual, and then we redo the step 4. This iteration enabled further refine and update the corner frequency FC1 and attenuation information T star for each of the target earthquakes. This is the 5th step. Then the last step involves the retrieval of the empirical attenuation function. Using the updated corner frequency FC1 and the T star from previous step, we compute the model and a model without the exponential attenuation term, shown by this equation. In this example, the black curve is a row observation of the displacement spectrum. Black curve represents the displacement model, and the red curve depicts the model without the attenuation term. By taking the difference between the black row data and the red model, we extract the empirical attenuation function from all the components, like this, and align one-to-one with the target events from for both columns, like this. Then we come back to the low-frequency earthquake spectrum, the black curve. We correct it by subtracting the averaged empirical attenuation functions obtained from the event that closest to the depth range of LFEs. This refinement reveals an intriguing observation that previously unexplained fall-off rate in LFEs by omega square fall-off are now well represented by the omega square fall-off rate. The corner frequency of low-frequency earthquakes appears to slightly increase from its best fit around 1 Hz to now approximately 2 to 3 Hz. While this corner frequency of low-frequency earthquakes with a magnitude less than 1 remains still lower than that of regular earthquakes. Therefore, we are able to say that the absence of high frequency component in low frequency seismic events can only be partially explained by the local attenuation and path effect. The source of LFEs is different from regular earthquakes. So we analyzed the structure and also the how much the attenuation can contribute to LFEs to understand the still mysterious different source of LFEs. We try to probe their source time functions. Taking the largest LFE in the orange columns as the target earthquakes, we are able to identify two target main earthquakes and some EGF events from smaller LFEs with high signal-to-noise ratio and cross correlation larger than 0.7. Here shows the waveforms of the main LFE waveform and the EGF functions. And here are the spectral ratio, like a plateau with first corner frequency and second corner frequency extra. After having decomposed the EGF from the target LFE, we found that the source time functions of LFE exhibit similar earthquake-like puzzles, while with notably prolonged duration compared to regular earthquake here, even longer than those of a regular earthquake of 3.3 magnitude. The duration is much longer than a regular earthquake. These findings suggest again that the low frequency earthquake source is significantly different from the typical regular earthquake source, and attenuation is not solely responsible for the distinctive spectral signature of low frequency earthquakes. The distinct faulting source is likely influenced by the unique faulting environment that host low frequency earthquakes, as what I showed in the vertical structure control that with fluid-rich subducting plate boundary. So based on this previous analysis of seismic structural control along the path of low frequency earthquakes and the existence of distinctive earthquake-like sources, we propose this schematic structure, which shows that the source region of LFE exhibit distinct characteristics, notably high pore pressure, high pore fluid pressure, marked by elevated QPQS and VPVS ratios, combined with an impermeable layer overlay. The dehydration of the downgoing oceanic crust likely facilitates these slip regimes by increasing pore fluid pressure and creating the necessary stress condition to host the LFE at the plate interface. The saturated fault condition that should govern this atypical rupture mechanism and stand as a crucial element in explaining the genesis of low frequency earthquakes. To wrap up this talk, I'd like to leave you with some very simple short takeaways. In this comparative study in Nankai region, there is a notable structural anomaly in the LFE source region with high VPVS and QPQS ratio, indicating the existence of high pore fluid pressure. The source time function of LFE shows earthquake-like pulse, but with longer duration. The abnormal source zone with high pore pressure right above the plate interface appears to govern the typical rupture mechanism and generate this earthquake-like source of LFEs. Attenuation definitely play a role in explaining this high frequency fall-off of LFE spectra. And the corrected LFE spectra is well following a omega square fall-off rate, while the distinctive characteristic of LFE, including the relatively small corner frequency and the prolonged duration in the source time function, sets them apart from regular earthquakes. And this six-step empirical attenuation function EAF method offers a means to extract precise local paths and attenuation effects. This method is not only limited to LFE analysis, but also applicable to some source property studies for regular earthquakes. Okay, this concludes today's presentation. I appreciate your attention, and I'm happy to take any questions you may have now. Thank you.
Thank you very much, Qingyu. That was great. I'll invite everyone to unmute themselves and join in thanking Qingyu for a great talk.